everybody, it's Santina and Will from Revelry Cycles on another rainy day in Sydney. This rain, that's killing us. Thank you so much for joining us. We missed you last week. And when we last spoke, we were getting ready to go drag racing. And sadly, the last minute, they canceled our race and the entire race season.
But that's okay because there's a lot going on. There are some other announcements coming up. We're involved in some other projects. We are going to be building some other bikes, so we've got lots of stuff to cover in upcoming videos.
Lots of irons in the fire.
Lots of them.
But today, we're here to talk about cylinder heads. So,
let's get into it. In previous videos in this series, we've covered a number of different ways to increase your engine's efficiency. We've shown you how to increase the bore, allowing the piston to displace more area so you have more volume to fill with fuel and air. We discussed altering your camshaft timing and lift to allow the valves to open sooner, open further, and stay open longer to move more air fuel into and out of the combustion chamber. And today we're going to show you the cylinder head and its role in bringing air into the combustion chamber, maximizing the atomization of the fuel in the air mixture as it's compressed, helping manage the heat that's generated by combustion, and getting rid of the spent gases.
let's look at the cylinder head's parts as they relate to that process. When the valves are open, it's the size and shape of the ports that determine the volume of air flowing into and out of the combustion chamber. When the valves are closed, it's the shape of the combustion chamber in the cylinder head, along with the shape of the crown of the piston, that determines the air's turbulence in the combustion chamber as it's compressed. This has a dramatic effect on the atomization of the fuel molecules in the air. Then there's the placement of the spark plug. This affects how long it takes the flame front to burn the compressed fuel-air mixture. A flame propagating from the center takes less time to burn all the way across the crown of the piston, as it has less distance to travel than a flame propagating from one side to the other. The Royal Enfield Twin uses a pen-roof combustion chamber. The pen-roof design, similar to a Hemi, has a spark plug located in the center of the chamber between the intake and exhaust valves. This design is commonly considered to be among the best for performance engines. The position and angle of the valves allows for better airflow around the valves and cross-flow of the air-fuel charge during overlap. This design also offers good surface to volume ratio and allows a very short, straight exhaust port. This, combined with the distance between the intake and exhaust valves, limits heat transfer and produces better thermal efficiency. This means you waste less of the energy potential of the fuel, so that more of that potential can be used to make power. When you increase the bore, you create a squish area, the portion of the head's deck that's outside the combustion chamber, but exposed to the bore. This creates turbulence that pushes the mixture towards the center and increases the efficiency of the burn as the piston moves towards top dead center. The Royal Enfield Twins are a 4-valve per cylinder design. There are several advantages to a 4-valve design. First, 4 valves per cylinder means better airflow. Mathematically, breaking a single 56 millimeter diameter intake valve into two 28 millimeter diameter valves results in a 50% increase in airflow into the engine. This additional flow is especially useful at high engine speeds to make better top-end power. Next, because the small valves are lighter, less mass means less reciprocating inertia, which puts less stress on cam and valve train components, and they can move more easily at high speed and reduce valve flow, allowing the engine to rev higher and produce more power. Then, this configuration allows placement of the spark plug in the center of the head. More rapid flame propagation leads to more efficient combustion, and once again, more power.
All right, as you can see, the original equipment Royal Enfield twin cylinder head is really a very efficient design by default. So how do we improve on them? Well, by reshaping and increasing the size of the intake and exhaust ports, we can dramatically increase the engine's ability to breathe. Using CNC, we can produce very consistent results in cylinder head porting and combustion chamber shape. The CNC process helps eliminate irregularities and inconsistencies that can occur from core shift in any cast alloy cylinder head. CNC also means that we can process a cylinder head in much less time than it takes to hand port it, which makes CNC a far more cost-effective process. So, what are my options? Today, there are really two that we know of. First, S&S offers a CNC cylinder head porting service where you send them your core cylinder head and they'll send you back a beautifully finished cylinder head with nice progressive increases in flow across all the lift points. That's what's currently running on our drag bike, and we're very pleased with it. And if you're in North America, that part of the world, I would strongly suggest that you just send your cylinder head to them, let them process it. There were only a couple of issues with that for us, and first was the cost of shipping. It actually cost us more to ship the cylinder head from Sydney to Wisconsin and back than it would have to purchase a new cylinder head, which was kind of an ouch, kind of an awakening moment. The other thing was when we got it back and tested it, we discovered a couple of interesting things. One, the exhaust flow was up dramatically, and the intake flow was about as good as it could possibly get with the existing valve diameters, and it was still not an improvement sort of at the level we were looking for. For bigger motors, we needed the intake to flow more, and we'll show you some of those flow numbers and break down for you what that means and how it works. But at the end of the day, we really needed much more intake flow than we were able to get with the standard diameter valves, no matter what we did with the ports. So we developed a big valve cylinder head, and it does require changing the intake seats, but we still use the standard exhaust seats, but we do use bigger intake and exhaust valves. When we process these, you also have to have the throttle body adapter attached to the cylinder head because the CNC actually cuts that adapter and matches it to the port while it's at it. The other difference is that we recognize shipping these heads around, depending on where you're coming to and from, can be awfully expensive. So we offer the option for you to send your cylinder head to us and we'll process it, turn it around, put big valves in it, the whole thing, send it back to you usually in 2 to 4 weeks. Or we offer just a brand new cylinder head with brand new throttle body adapters, CNC, cut, done, big valves, shipped to your door, and that's it. So, what kind of performance improvement can I reasonably expect? Let's take a look at some of the test results.
Let's start with exhaust flow. This is the stock Royal Enfield exhaust port. First, I'll point out that the max valve lift of the S&S cam is 354 thousandths of an inch. This means that the total range of valve lift of this cam is covered by the first 7 lift points on our charts. These tests go out for more lift points to 500 thousandths of an inch, obviously because we want these heads to work with higher lift cams in future projects. Now, you'll notice that the flow comes up very quickly as the valve opens. By the second lift point of the 7, the flow is 63.4 cubic feet per minute, or CFM. That's almost half the 128 CFM flow we see at max valve lift. This good flow rate at low valve lifts allows higher exhaust velocity, and the flat floor or D shape of the port makes the velocity more constant. All in all, this is a reasonably efficient design right out of the box. The S&S CNC ported head, as you can see, comes up just as quickly to roughly the same flow by the second lift point, but then ramps up flow dramatically. By the fourth lift point, 201 thousandths of an inch, it has exceeded the total max lift flow of the stock port. Then at max valve lift, it is a whopping 156 CFM. That's a 22% increase in exhaust flow over stock using stock valves. This is the exhaust flow of our big valve cylinder head. You can immediately see the effect of increasing the valve diameter. At the first lift point, it flows 30.2 CFM. That's a 7.5% increase over stock. This then carries all the way through the lift ranges. By the fourth lift point, we're at 137 CFM, well over the max lift flow of the stock valve and port. Then, out at max lift, the Revelry head, with its bigger valves and reshaped ports, allows a 33.6% increase in exhaust flow over stock. Given how efficient the stock port is, that's a lot. Now, let's have a look at the intake flow. The stock intake flow rises at basically the same rate as the exhaust across the first 5 lift points. This indicates that the basic shape of the port is pretty effective. The stock intake comes up to 154 CFM and roughly stays there through max valve lift. The S&S intake flow comes up on basically the same slope, but with an important difference. By reshaping the area just behind the valve seat, they get 29 CFM at the first lift point. That's 10% more flow the instant the valve opens. Then, by reshaping and removing obstructions from the port, they get 167 CFM at max valve lift. That is an 8.6% increase in intake flow over stock. When compared to the 22% increase in exhaust flow, that doesn't sound like a lot. However, when you consider that mathematically, given the diameter of the intake valves at the flow rate of our tests, about 170 CFM is all you can reasonably hope for. This means the S&S CNC heads are basically as good as you can get at the stock intake valve diameter. Before we move on, let's consider another factor. In the stock head, the exhaust flow average is 86% of the intake flow. The general rule is you're looking for exhaust to flow 80 to 90% of the intake, so this is pretty good. The S&S exhaust flow average is 96% of the S&S intake flow. You can see how far apart the two blue stock intake and exhaust lines are, and how close together the two orange S&S exhaust and intake lines are. The fact that the ported exhaust flows basically as much as the ported intake is another indicator that to increase intake flow in a bigger motor, larger intake valves are required. The larger diameter valves allow the Revelry Racing big valve intake tract to flow substantially more from the very first valve opening all the way through to well beyond the max valve lift of the S&S cam. And you can see how broad and smooth the flow curve is. This is what allows the cylinder head to make both broad torque and lots of horsepower at higher revs. At the max lift of the S&S cam, the Revelry Racing head allows a 32% increase in flow over stock, and at the max lift point of our tests, it goes up to 37% increase. To get the exhaust flow back to where we want it, we also need to increase the size of the exhaust valve. The Revelry big valve exhaust flow is 89% of the intake flow. A good cylinder head combined with the right throttle body, cam, and timing is the key to unlocking the true potential of all other performance modifications you make. For the sake of a one-page comparison, here's a stock cylinder head, intake and exhaust, as compared to an S&S cylinder head, intake and exhaust, as compared to the Revelry Racing cylinder head, intake and exhaust. As you can see, the big valve head flows much better from the very first lift point. That's a 19.2% increase in intake flow and 7.5% more exhaust over the stock head at the first lift point. Then it progresses all the way up to a 37.9% increase in intake and 36.9% increase in exhaust flow over stock. Now, let's have a look at how the additional flow translates into power. It should be noted that, as we said before, the original cylinder head is pretty good. These increases in flow don't really net any significant performance benefit at low engine speed and under light loads. It's under heavy load and hard acceleration that you'll feel the difference. It's also important to understand that a bigger bore produces more velocity through the port and more swirl around the valve opening. So the bigger the engine, the broader the range of benefit you'll get from bigger valve CNC heads. Smaller engines can still benefit from bigger valves, but you'll need to turn faster, higher RPMs, to really make the most of them. Bigger engines, however, need better flow, particularly intake flow, to unlock their full potential. These cylinder heads can deliver a broad range of torque and power depending on how the components around them are configured. There are several variables involved in tuning the cylinder head to do various things. The first dyno chart we're going to show you is an 865 motor with the big valve cylinder heads, a stock throttle body that's bored to 36 millimeters, and the cam timing advanced 2 degrees over the S&S specification. You can see that the engine makes 70.58 horsepower at 6,230 RPM and 64.81 foot-pounds of torque at 4,850 RPM. That is stump-pulling, tractor-like torque. This torque is the result of combining the smaller throttle bodies, which make higher velocities at mid-range, and advanced cam timing. Advancing the cam timing, among other things, also increases combustion chamber pressure at lower engine speeds, brings the torque curve down much lower in the RPM range, and makes the torque curve stronger. This configuration puts the bulk of the usable torque and horsepower between 4,500 and 6,500 RPM and is ideal for a bike that pulls hard in the upper mid-range without revving too high, like a flat tracker. With every configuration, there is compromise. The downside of this particular configuration is that around 6,500 RPM, both the horsepower and torque start to drop off pretty quickly, so you wouldn't want to run this configuration in like a road race bike. Now let's look at another 865 engine with the same cylinder head, but this time with a 40 millimeter billet throttle body and the cam timing retarded 4 degrees. As you can see, this engine doesn't make as much torque as the engine with the smaller throttle body and advanced cam timing, but it makes a lot more horsepower. It also brings the torque to 55 foot-pounds and it holds it there right up to max RPM. This broad, flat torque curve gives you stable, controllable torque whenever you twist the grip, combined with lots of high RPM horsepower. This configuration is much better suited to, for example, a road race bike. We should also mention that after this dyno pool was done, we turned the rev limiter on this engine up to 8,500, and it still pulls strong over 8,000 RPM. As you can see, with the same engine and the same cylinder head, you can tune the bike to do dramatically different things based on what you need that engine to do. Alright, we get so many requests for this kind of thing, we're going to let you hear one of these engines with a 40 millimeter throttle body and the cam timing retarded for top end power. Here we go. So we were ready to go racing. We've done so much work to this motorcycle during our COVID lockdown and breaks. It's kind of like she's all dressed up with nowhere to go. And a great deal of you have asked to hear it, so I give you my drag bike. There you have it. Thank you so much for joining us. We hope that you enjoyed our video all about cylinder heads and that you learned something new.
Next we'll be doing throttle bodies because as you saw from some of the performance numbers and things, throttle bodies and cam timing are an integral part of how you make these cylinder heads work. And there's even the possibility we may do a cam timing video. Sort of depends on how many questions we get. We'll see how that works out. If you'd like a set of these cylinder heads and you want to just buy this new cylinder head ready to go, there's a link below to do that. If you want us to process your cylinder heads, that's a little more involved, so you should either ring us or send us an email and we can make that happen.
Absolutely. We hope that what you have seen so far with this series is that we're trying to get you to make a plan for what you're going to do to your race bike. We understand that not everybody can just sort of go from a stock motorcycle to a full drag bike, and that sometimes you've got to piece it together. But we want you to make a plan and then piece by piece work your way towards it. So this week in the comments below, we want to know what's your plan and what have you done so far to get to your end game.
Yeah. And we hear a lot of, we've had some feedback, oh, why would you do this to an Enfield? Enfields aren't race bikes. Well, we don't agree.
At all. There is a long history of racing with Royal Enfield going back decades and all kinds of racing.
Well, yeah, even recently, a year ago, Royal Enfield did a land speed record. The factory did a land speed record. The Harris Performance fellows have done some road race bikes. There's flat tracking. There's the Build Train Race series in the U.S. where they've just done flat tracking and now they're going to do road racing.
And with the flat track team, they won on their 5th race in their first season.
Yeah,
Amazing.
Royal Enfield won an American Flat Track Pro race in their first season. So flat tracking is going to get real.
Good job to them.
Yeah, good job to
that
them.
is bloody hard work
Yeah,
and
no
a
kidding.
really, really good result.
Yeah, so we're tickled. And there's, there's lots of racing going on.
Lots. And oh, by the way, drag racing is like the best, most good fun thing I've ever done in my life, and there is no way I'm not going to do it. And look, we're not saying everybody should race. These are fantastic motorcycles. If you want to ride a stock bike around the world, go for it. It will absolutely do that, and it'll be so much fun.
That's it.
But racing is a normal part of Royal Enfield history.
And it's all about having fun. So remember,
If you ain't having fun,
you're doing it wrong.